Okay, so this is, yes, macrofinance segmentation and heterogeneity. It's really based on work with Gautam and with Jojo. I'm not sure, is Jojo here? I haven't seen him around, so yeah, but a very outstanding PhD student here at Princeton. Okay. So if we look back historically, we see that the way the government has organized the financial sector has varied enormously over time. To take one stylized example that's often kind of given, if we go back into the second half of the 19th century, the government set up a system where insurance companies were actually fairly unrestricted in terms of what kinds of assets they could hold. By contrast, the banking sector was enormously restricted. The national banks were not able to make mortgage loans, except for one case against farmland, where it was a 5-year loan. They had to hold US treasuries, particularly long-term US treasuries, in order to finance any money creation. And really, in terms of commercial loans, they made short-term commercial paper. So it was a very particular system, where there was actually very little duration mismatch on the bank balance sheet. FDR and the New Deal completely reorganized the way the financial sector operated and moved to a system where actually the banks would make very long-term loans, in particular these 30, 40-year fixed-rate mortgages, and hold a range of long-term assets. And that's when we get this kind of maturity mismatch in the banking sector that is so often focused on in macrofinance. That's when we really see that emerging. By contrast, in the insurance sector, that was increasingly clamped down, and insurance companies were increasingly asked to match duration and hold long-term government or corporate bonds. There's a lot of evidence from Moto's work, from my work with Barlint, that the way you put these restrictions on the financial sector is extremely important for trying to understand asset pricing. Right? When these institutional constraints bind, often determines when you get price over or under reaction in response to certain kinds of shocks. So this has generated a lot of interest in trying to understand how does all this stuff happening in the institutional asset pricing area, how does all of that really affect households? Who wins and who loses based on the way that you organize the financial system? Okay? This is an interesting but tough question. It's been tough technically for people to try and answer it because it requires high-dimensional modeling, and the task that I've taken on with Gautam and Jojo is trying to make progress on that. Before we get into the model, let me ask you a question. Right? If we think about these two kind of stylized examples, what do you think? Would you, if you were the regulator, would you set up a system where financial intermediaries can participate in whatever asset market they want? Or would you try to segment in some way and say banks in this market, pension insurance companies in a different market? What do you guys think? I want to get a sense of your prior before we go into the talk. Have you ever thought about the question before? Someone, what do you think? Anybody want to give a thought? Go for it. That's a great answer. So one thing we see particularly is if the government really wants to create captive demand, then they do want to segment, right? So it depends a bit what their objective is. But you've seen a lot of planners today that are benevolent, right? This has been the theme of the planners in today's talk. I don't know if I'm entirely sympathetic with that view of the government, but nonetheless, that's been the dominant view here. So if we take the benevolent planner trying to maximize household welfare, what do you think in that case? How would you make this decision? So why is that? Why would that help? Oh, can I repeat the question? Yeah, so the question is, or the answer is, how about the how about a narrow banking system where the banks just hold short-term securities, and that means the insurance pension funds take on essentially all the risk in the economy, right? So why is that attractive? Okay. Any other thoughts? Oh, I have to repeat the answer. This is really not set up for Q&A, Markus. Okay, so the idea is the narrow banking system encourages stability, and people expect stability. It's a behavioral answer that we need stability because people expect stability. Yes, go for it. Because bank deposits fundamentally short-term, you should restrict what the banks can do. Okay. Well, these are all great answers. So once we move this into the model to give a sense of the punchline, the end answer is going to depend a lot on who is really exposed to recapitalizing the different sectors, right? So we're going to end up in a model where it's really the lower income households that are very dependent on the pension insurance sector. And the wealthier households are much more independent. So if you load a lot of the risk into the pension insurance sector, it's really the lower wealth households that end up being really forced to do this recapitalization and hurt. So in some sense, putting the risk in the pension insurance sector is going to have very big implications for inequality. That's what's going to come out as the end punchline. But we can return to this once we've seen the model. Okay. So in terms of the structure for today's talk, it's going to take us a little bit of time to get back to this question. So this is partly a teaching talk. So I'm going to start with something more like a teaching model, right? This is the model one, sort of an illustrative heterogeneous agent macrofinance models. I'm not keen of acronyms, but if you really want an acronym, it's a HAMF model. I don't know, I'm not sure what the fashion for acronyms is, but so this is really going to be an attempt to take the kinds of environments that you've seen today and introduce heterogeneous agents. Okay? So it's going to be a model where you've got heterogeneous households, there's one long-term asset that's capital stock, and there's going to be a financial expert. And I'm going to use this model as kind of the teaching environment to show how we can set up equilibrium and how we can characterize it using the deep learning tools that Gautam introduced very well in the previous talk. Okay? And we can use this to say a little bit about how limited household participation in markets relates to asset pricing and inequality. Okay, that's going to be the teaching model to kind of understand how we do this stuff. Then, if we have time, we're going to get to the bigger model, which will be the actual institutional asset pricing model. And here we're going to enrich it to have different types of intermediaries, banks, insurers, and we're going to have multiple long-term assets. We're going to have long-term insurance contracts, we're going to have government bonds. And in this, we can actually revisit these historical episodes and think about what would the optimal segmentation look like? How would you want to decide which kinds of markets you want these different financial intermediaries to participate in, and which types of households win and lose in that situation? Okay. Does this make sense? Are you excited? Well, that was a lukewarm, lukewarm response. Okay. Okay. In terms of literature review, I mean, my research is very much on the macro design of the financial sector. Here it's very much thinking about how the design affects inequality. I have other work thinking a lot about how it affects government financing capacity. But that's the general theme of what I try to work on. How does the way you set up the financial sector really matter? And how would you choose that design problem? Okay. Oops, this is... Right. So let's start with this first model, the heterogeneous agent macrofinance model. So like all the talks today, it's going to be a continuous time model. It's just going to be one good. It's produced by an AK production technology, where this E to the Z is the productivity, and Z follows a mean reverting TFP process. Okay? So a very plain vanilla kind of model. As usual, capital stock has adjustment costs, where phi is the amount of capital you get if you do investment at a rate iota. Okay? The same model you've seen, but with a mean reverting shock rather than a stochastic depreciation shock. The economy is populated by a collection of overlapping generation households, okay, which we're going to index by I. These households get idiosyncratic death shocks at a rate lambda h, and when households die, they're replaced by a new household with some initial starting wealth, var phi h a, right, where a is the aggregate wealth in the economy. Okay. While the agents are alive, they get CRA utility from consuming. And there are two key frictions on the household side. As is typical in OLG models, the agents are not able to contract across generations. Once we move to the richer model, we're going to introduce the insurance sector in order to facilitate that contracting, although in a frictional way. But here, there's no contracting across generations. And to capture the idea, or what we see in the data, that households with different wealth end up choosing different portfolios, we're going to introduce a penalty. Okay? So you have a penalty on holding capital, where the more capital you hold, the higher the penalty. The less wealth you have, the higher the penalty. Okay? This is a simple way to capture a participation constraint on the household sector, that the more wealth they have, the easier it is for them to directly engage in capital markets. There's no micro foundation here. This is a hard assumption. Just to get this feature, the poorer households are going to be very dependent on deposits, whereas the wealthier households are going to be able to be directly holders of capital or do entrepreneurial activity in the economy. Does this make sense so far? Okay. So then, as you've had in the models today, there's going to be a financial expert, has a death rate lambda E, log preferences, and as usual, they have a constraint that they can't raise equity. Okay? There are competitive markets for everything in this economy. In particular, there are going to be risk-free bonds in zero net supply at interest rate R, and then there's going to be capital with a price Q and a return RK. Okay? So as you've had throughout this institute, we're going to, or initiative, we're going to have that we denote the drift of the price process by mu and the volatility of the price process by sigma. And where appropriate, we're going to work with the return on the price process or return on the capital stock, where RT is the average rate of return, and then sigma Q is the stochastic component of the return on holding capital. This is the whole model, at least for the first part of the talk. Tried to strip it back as close as I can get, do a heterogeneous agent version of what you've seen so far. Is everything clear? There should be a dt in the first term. Yes, there should be a dt right there. Yes. Okay. So let's set this up. So we're going to spend a bit of time trying to show how we would characterize this equilibrium and make sure we're all clear about it. So let's start with the optimization problem. Okay? So standard rational expectations problem, where given beliefs about the price process for the interest rate and the price, a particular household with wealth, holdings of bonds plus the holdings of capital, they want to maximize their lifetime utility of consumption minus any costs they have for holding the capital stock, subject to a very standard looking budget constraint, where as usual I'm going to use mu A and sigma A to denote the drift and volatility of the agent's individual wealth. The problem for the bank or the expert looks completely the same, except for the fact they don't have this cost on holding capital. And I've not got Epstein, I've got log preferences. So then if we go for equilibrium, what's equilibrium going to look like? Well, of course, given their beliefs about the price processes, the households and experts, they optimize. The prices then solve market clearing, and then agent beliefs need to be consistent with what happens in equilibrium. Okay? Here we have a goods market, a capital market, and a bond market. So far, so good? Okay. So we want to set this up recursively, right? That's our goal here. Even though we've got a distribution, we want to work with a recursive formulation. So we need to think about where we would have non-degenerate distributions in this economy. So first of all, we can think about the expert sector. The expert sector looks the same as the models you've done so far, right? There's log utility, there's no restriction on their portfolio choice. So for them, we're going to have that their portfolio choice does not depend on wealth, and you can aggregate the sector the same way you've been doing all day. The households, however, that's not so simple. For the households, we're not going to get an aggregation result. For the households, we're going to have to keep track of the distribution of wealth. Why do we not get an aggregation result inside the household sector in this simple economy? Which assumption? Right, so this psi function is what breaks this result, right? So the reason you can get aggregation in the models you've seen today is it doesn't matter how much wealth the agents hold, they make exactly the same portfolio choice, right? The share of wealth doesn't depend on their wealth. That's explicitly what we're trying to break here when we introduce this cost of trying to hold capital. Okay? And so that's why we end up with this non-degenerate wealth distribution across the household sector. Okay, so that means that if we think about the state space, the individual household state is A. The aggregate states are going to be Z, K, and G, where G here is the household wealth measure. And so if we integrate over the G, we're going to get the total household wealth share. The key thing is when we think about the beliefs, right? The agents are going to work with beliefs that have to be true in equilibrium. once we move recursively, beliefs about the price process really become beliefs about the evolution of the distribution. Because if you know the distribution evolution, you know what the prices are going to look like. Okay. So given all of that, we can now characterize what this equilibrium is going to look like in terms of 3 blocks. The first is the distribution evolution. The second is the agent optimization problem. And the third is the equilibrium consistency. Okay. All right. So let's start with this block 1. Okay. First thing we need to think about is the distribution. If I understand correctly, you haven't done a KFE yet. Is that right? Yeah, you haven't done it so far? Okay, so this is I guess, the different part of this model relative to the models you've been solving so far today and yesterday. So here we have to think about what this distribution of agent wealth is going to look like. Okay, so the household wealth measure is going to have a collection of drift terms. So part of it is going to be the birth process, right? So when agents are born, that introduces mass into the distribution. When agents die, that takes mass out of the distribution. Okay, that's the first part. Then we have the evolution of the density G coming from the wealth drift. Right? So as mu moves up, that means there's more mass further up, and so we get a negative drift in the density. We get the volatility term. So having more volatility spreads out the wealth distribution. Right? So higher volatility means more dispersion in the way that G is moving. And then finally, we get this aggregate shock component, right? So here we have that the TFP process directly hits the asset prices the households potentially hold. And so that puts a shock in the wealth of the individual, an aggregate shock to the individual wealth of the households. And so this means that the distribution is going to be hit by this TFP shock in the economy. Does this make sense? Right? Can you see how these different components come out? Okay, so question for you guys. If you hadn't seen it, how would you derive the KFE? And I'm not looking for the answer. Look at Ben Moll's notes. Make an educated guess of how it should be different. If you have a new problem and you want to get the KFE, how would you systematically get a KFE? Any thoughts? Without Ben Moll by your side. Any ideas? Tough question. Anybody from along here? I guess you know Sebastian, since we wrote all these appendices together. So I can't ask you, I guess. The way I usually go about KFEs is the following. So I use this so-called propagation of chaos technique, which I'm going to sketch out briefly in a couple of slides. I am going to skip some of the details, so you can see there's a couple of points where I'm not a little bit loose. That's just to save time. But I think the simplest way normally to get a KFE, particularly when you have both idiosyncratic shocks and aggregate shocks, is to study the dynamics of the finite agent population and then take the limit as the number of agents goes to infinity. I think that's normally the easiest way to do it. So in this case, we'd start with a finite agent population with n agents. And if we think about n agents, where when an agent dies, a new agent takes their place with the new wealth, okay? Then we would have that the wealth of a particular agent in the economy would look something like the following. They would have their drift, they would have their volatility, then if they die, they would lose their wealth, and then the new agent would come in with the new wealth that they're born with. And then we do also have this term that would be any transfers or taxes related to recapitalizing the new initial agents, although I'm going to not be very specific about that because in the end I absorbed that into the mu A in the KFE I wrote down before. Okay, so that would be our evolution of a particular agent in the economy from the point of view of trying to take this limit. We can then think about an empirical density, right? So I can count up the positions or keep track of the positions of all the different wealth levels in the economy. That gives me an empirical histogram or empirical density for what the distribution of agent positions look like. What I want to do is I would like to use Ito's lemma to get the evolution of G, and then I would like to take the limit as the number of agents goes to infinity. That's what I'd like to do. Right? The catch here, though, is that it's very hard to differentiate a direct delta function, right? So here, this is a direct delta function as an indicator for an agent position. So to make our life a little bit easier, instead of trying to differentiate this direct delta specifically, we would instead take these test functions, which are smooth, compact functions, right? Compact supported functions. And then we would apply phi to these indicators so that instead of trying to differentiate this complicated Dirac delta thing, we'd instead try to differentiate this object here, right? Okay? It's like a smooth version of the empirical density function. Okay, so second step, let's do that. Okay, so I have my smoothed empirical density, smoothed by these test functions. I can apply Ito's lemma, and I can rearrange a little bit. So there I get that the evolution of the density over some period of time t. I get my time derivative, I get the drift term, I get the volatility term, and then I get this idiosyncratic term, right? Across the population, the agents die at some idiosyncratic rate, Poisson rate ni, or according to a Poisson shock ni, in which case they lose their wealth. Okay? So I get this idiosyncratic component here. And then I also have this aggregate shock that's going to hit it, plus I have any transfer terms, although I'm just going to leave that at the moment and focus on this instead. So when we take the limit, as the number of agents goes to infinity, all the idiosyncratic noise in this equation averages out. Right? Once I have an infinite number of agents, I no longer have a sum over a collection of idiosyncratic shocks. So this term becomes an average, and any transfer terms would also become an average. And so it just ends up here in the flow. And more importantly, if I think about the agents dying, okay, they die at some rate lambda h. So instead of having this sum over these idiosyncratic shocks, we instead just get lambda h, the death rate, times the density here. Then for the rest of them, for those, as I take the limit, all of these sums become integrals. Okay? But the key thing is the idiosyncratic noise averages out, so we lose all these stochastic terms, but the aggregate noise does not. Right? The aggregate shock remains, and so we keep this aggregate dW term in this KFE. Okay? So here I have the equation. At the moment, it's written in terms of derivatives of the test function. I'll leave it as an exercise for you to finish the proof by integrating by parts, swapping the order of differentiation, and that will get you back to the KFE. Okay? High level, though, I think the way to always think about KFEs is start with a finite population, find the way to take the limit, see how the idiosyncratic noise averages out, the aggregate noise does not, and that's the foolproof way to get the KFE. Does this make sense? I know it's hard to absorb just from here, but hopefully you'll go away and try it, or you can look at the appendix of my paper with Sebastian, and you'll see a fairly detailed, fairly detailed proof of this. Yes. Well, that's a great question. It's going to relate a lot to how we're going to solve this with a neural network, because ultimately we can't work with the continuum. We're going to have to take some kind of finite dimensional approximation. And to jump ahead, oh, this is a terrible system. So can I just make an observation? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have like 15 microphones in this room, don't we? Aren't these? So the question was, when we take this limit, why do we start with a finite number of agents rather than a discrete state space or some other finite dimensional approximation? Which is a good question. And it relates a lot to what happens when we try to approximate the distribution to take it to the neural network. Right? And we could do that as well. Right? Ultimately, this is going to turn out to be very convenient for the asset pricing. We'll talk more about this later. What we're in the end going to do is we're going to think about using a limit where we keep this limit, right? So we take the limit for all the idiosyncratic noise, but we don't take the limit in terms of the number of agents. And this hybrid KFE is going to turn out to be pretty powerful for trying to solve these models. And that's what we're going to do in the end. But in terms of the proof, it's not unique. There are other ways you could prove it. Okay, great question. Any other questions? Was that clear, or is it completely, have I lost everyone? Okay, I got 5 nods. I'll take that as a victory. Okay. So the second block is agent optimization. Okay, so the first block is always the distribution evolution. Second block is agent optimization. So for the agent, we have an individual state, and then we have the aggregate state Z, K, and G. Okay, where K is the aggregate capital stock, Z is the TFP, and G is the distribution across the households, where of course the residual is the wealth share of the expert. Okay, so I'm going to let S denote this aggregate state. Once we move to this recursive formulation, from the household's point of view, they have a belief about the evolution of G, right? So we just wrote down this Kolmogorov forward equation, right? I'm going to use mu G to denote the drift of the KFE and sigma G to denote the volatility term in the KFE. So agents, they need to have a belief about what the drift and volatility of the distribution are going to be. That's how they forecast prices. Okay? So given that, an agent wants to choose their consumption. I'm going to say they choose their wealth share in capital rather than the capital stock to be more consistent with what you did this morning. They choose their wealth share, and of course they choose the investment rate in capital. Okay? So they do that. They have their flow utility. They've got the cost of their portfolio choice if they hold lots of capital. And then we get a whole bunch of pretty standard terms. Okay? The black terms are very similar to what you've seen so far. But then we get these very nasty looking green terms, right? So these green terms are the Frechet derivatives with respect to the evolution of the distribution. So ultimately, if I'm trying to think about what prices are going to be in the future, I have to forecast what the distribution is to understand what those prices would look like. So what we care about is, as the distribution changes, how does my value function get affected? Right? So I have a belief about how distribution is going to evolve, drift and a volatility. And based on that belief, I'm thinking about, well, then how does my value function change as this distribution evolves? So that introduces these 3 green terms, 1 which is the drift component and 2 which are related to the volatility. And it's really these green terms that have caused all the trouble for macroeconomics, right? If we didn't have these green terms, life would be a lot easier and the heterogeneous agent macro would have been resolved 30, 40 years ago, right? The problem is that these terms are very hard to deal with because here we're taking a derivative with respect to a distribution. So it's an infinite dimensional derivative. And that's very, very hard to work with computationally. Okay? And so we have to make progress on finding some way to handle these derivative terms. And ultimately, that's what the neural network and the high dimensional solution techniques are going to open up. Does this make sense? Yes, go for it. I said what? The distribution. G is the state, yes. Yes. So what I was thinking this is how it evolves. Right? So it evolves, but it depends on the agent decisions, right? So for an agent policy and how their wealth will evolve, this is how the law of motion of the distribution evolves. Okay? So this is rational expectations. So far, it could be any belief process. I've just said that for a given belief process, this is what they would do. Rational expectation says that the equilibrium belief, the equilibrium law of motion for G that emerges in the economy, given the decisions the agents make, is indeed what they believe would happen. Right? Agents have correct beliefs about the law of motion for the economy. This closes the model, and this is what makes life so difficult, right? Because it's a fixed point problem, right? To know the KFE, I need to know the agent decisions, but to know the agent decisions, I need to know the KFE. So I have to solve this infinite dimensional distribution at the same time. This is what makes life so hard. Okay? But also exciting, because we can solve rational expectations models. Yes? So the question is that the fact that we don't have an aggregation result does not relate to the fact we don't know how the distribution evolves. Is that right? Well, the reason we don't have an aggregation result, yes, it's separate. It's because ultimately the agents have a distortion in their portfolio choice. So agents with different wealth levels choose different portfolios because they face a different penalty. So this means that because every wealth level has a different portfolio, we can't aggregate up the way you've been able to do so far. So that's why we break aggregation. Do the agents know the belief process? Well, rational expectations is a world where they do know it, right? So we say agents, yes, they have a belief about what's going to happen, but in equilibrium, their belief about how the distribution is going to evolve is correct. So in that sense, the agents do have correct beliefs. I'm always going to work with rational expectations models. So it's always important that they have correct beliefs. We could think about deviations from rational expectations. The question was, is this important, right? That we have this belief process, right? So yes, I'm going to work with rational expectations. So in that sense, the fact that agents have correct belief about the distribution is always important. I think what you're reacting to, though, is the fact that a stated equilibrium as agents optimize given a belief, and then in equilibrium beliefs are correct. That's just a standard way to write rational expectations. There's no special thing about that. That's just a way of writing a rational expectations equilibrium. It's the same equilibrium you would always write. Okay, Markus. So I have a belief about how the wealth distribution evolves. And in equilibrium, my belief about how the wealth distribution evolves has to be correct. So as my advisor, Tom Sargent, would say, there's kind of like a communism of beliefs here, right? Everybody has to end up believing the same thing in equilibrium, right? So in that sense, we all believe the same thing, and what we believe is the true evolution of the economy. Great. So then the final part is the price consistency. So you guys are experts on this part, right? So we know that market clearing pins down the prices. The problem, though, is that for long-term asset prices, like our price of capital, it's only implicit, the way that the market clearing pins down the asset price. And so we have to also impose that it satisfies Ito's lemma. The drift and volatility of this price process satisfy our Ito functional form on the price. It's like a paparazzi. Okay, so, all right, so that's our equilibrium. Okay, so why is this hard to solve, right? So I'm going to try to make a bit of a comparison to some other models we do know how to solve. Okay? So if we thought about a representative agent asset pricing model, like a Lucas asset pricing model. So in that case, we'd have a representative agent, so we don't have to worry about the distribution. Okay? We would have one asset pricing equation. Because it's a representative agent, we can just plug in that C is equal to Y, and everything is pretty simple. And for that, finite difference is going to work great. Okay. We could go up a step in complexity, right? We could think about something like the Crusoe-Smith model, which you've probably done in your first year grad school. Okay. So that's a model where you have heterogeneous wealth because you have uninsurable labor shocks. Okay. So for that model, you have a non-degenerate distribution, right? You have to keep track of the distribution of agent wealth. You also have a non-trivial optimization problem, right? We can't get a closed-form solution to the Euler equation or to the HDB because we do not have that there's this scaling property. It doesn't mean that the way your wealth evolves scales with wealth, okay? So we can't solve the HDB in closed form. But the asset pricing in Crusoe-Smith is really simple because we only have short-term asset prices. We have a rental rate and a wage rate, okay? So if you look at the work with Jojo, with Sebastian, with Matu, we show how to use the neural networks to solve these models. We also have a whole bunch of models, like the ones you've been doing, where we have a low-dimensional distribution, maybe 2 dimensions. We have a closed-form solution to the value function, so we know the form of the value function in terms of your individual wealth. But we do have the complicated asset pricing, right? They have long-term asset prices. That's what Gautam was talking a lot about in the previous presentation. Okay? The difficulty here is to try to have complexity in all these different dimensions, right? To have a non-degenerate distribution, have an HJB that does not have a closed-form solution, and to have long-term asset pricing that's not trivial to work with. Right? That's what we're trying to bring to the table in this paper. Does this make sense? Okay. So how are we going to do it? Well, we're going to work with neural nets. This is going to build directly off what Gautam was talking about in the previous lecture. So I think as you get a sense of from the previous talk, the high-level idea here is we want to represent the first steps. We want to represent the agent continuum, but a high but finite dimensional approximation to the distribution. Right? So that's the first thing we want to do. Okay. The second thing is we want to find a way to represent equilibrium functions by neural networks with states as inputs. And we have to decide which objects do we want to approximate. And then we have to think about how we're going to train the neural network parameters to minimize the loss on the equilibrium conditions from randomly sampled points in the state space. Very much like what Gautam was describing. I would say at a high level, this is easy to describe. I think we've often found it tricky in practice. I think, Sebastian, you would have testified to this. One way to think about the art of deep learning is to try to think about how to rewrite the problem to help the neural network. There is another way, which is to try to get better and better training. I guess that's one direction you can go. I think in this paper, we tried a lot to think about how to simplify the problem to help the neural network along the way. Does this make sense? All right. So first question, how would you approximate the distribution? So let's come back to the question that we had a bit earlier. What are the different options we'd have for trying to approximate this infinite dimensional distribution? What tools do we have on the table here? What have you seen? So we could discretize the state space, right? That's the finite difference method, right? You've seen that quite a bit, right? So we could work with a discrete state space. We could work with finite agents. That's what I mentioned before. And I guess the third option would be to project the distribution onto a set of basis functions, right? That would be our three main options for trying to handle the distribution. So we actually compare these different options in a different paper. So here we have, yes, the three options. So we can work with the finite number of agents. We can think about masses on a grid and think about a Markov transition between the grid points, exactly as you were saying earlier. We could also pick a collection of basis functions and then think about the projection onto those collection of basis functions. If you like, that's a more general version of projecting onto the discrete grid points. So in each of these, we'd have a different kind of approximation to the KFE. Right? So for the finite agent, the KFE is really the evolution of the other agent states with all the idiosyncratic noise averaged out. Right? That's what we do for this one. For the discrete state, it's the evolution of masses between the grid points. You guys are all finite difference experts, so you know exactly how that looks, right? And for the projection, we need to use the KFE to get the evolution of these projection coefficients, which is quite a non-trivial task, right? It takes, well, in the end, we did it with least squares. I think Sebastian would testify that it took a fair bit of thinking to try to get this to work. It's quite non-trivial how you get the coefficients. The trade-off in some sense is the projection method is lowest dimensional, right? In that sense, it's very parsimonious and it has a lot of nice interpretation, particularly if you project onto the eigenfunctions, like what was done in the paper. The difficulty is that getting these law of motion for the phis is kind of hard, right? Working with this KFE is a complicated task. On the other end of the spectrum, we have the finite agent population where the KFE is particularly easy, right? Because all you need to think about is how are all the other agents in the economy evolving, which is a very easy kind of KFE to write down. And it's often why it's very appealing as the first thing to try in this case. Discretizing on the grid. In the examples we've done in these kind of models so far, it's proven tricky, I would say, in the sense that you need to get a very accurate approximation to the derivatives in the KFE, and that proved tricky in terms of needing a high dimensional space. It's not something we found to be overwhelmingly successful, although I have found it to be quite successful in search and matching problems. When I go and solve these search and matching problems and we don't have sort of the drift of the distribution in the same way, the sort of simpler KFEs, for those problems, this works extremely well, and for spatial models. So I think ultimately what technique you want to use, going back to your question, in some sense really depends on the model, right? If you have a model where the way the distribution affects agent decisions really depends on the shape of the distribution, right? So it's like a search and matching economy where I care about who I meet, or a spatial economy where I care about where I go, right? For those economies, I really care about the details of the shape of the distribution. And then I kind of need something like this. I either need a discrete state or a projection that really gives a really rich and nice approximation to the distribution. If the way the distribution enters is essentially through the mean, right? So I'm thinking about sort of the aggregate holdings of capital, for example, across the sector. Then in some sense, the details of the distribution are not as crucial for trying to get the interaction. And here, the finite population has worked extremely well. So I think it depends a lot on the model. There's not one approach that I think is dominant. I think it depends a lot on what you're trying to do, and particularly how the distribution enters back into the problem. One thing I want to highlight about the finite population methods, particularly convenient in continuous time, is that we actually can do it without a lot of agents. So we've seen a lot of discrete time deep learning solutions to Kruskal-Smith and these other models, and they have a huge number of agents. I think Malia has 1,000, maybe even 10,000. I think 10,000 agents, right? So 10,000 agents is a lot of agents. 10,000 derivatives to calculate is a tough thing to do. But actually, when you work in continuous time, we don't need to simulate, right? Because we're going to work with these analytical expressions. And so you don't actually need to have 10,000 agents to average out the noise, right? When people have finite agent approximations, the reason they need 10,000 agents is it takes a lot of agents to average out the idiosyncratic noise and get a good simulation. But what we do is we do that analytically. So if we go back to our KFE approximation, here I have the step in the derivation, right, where I've got the n agents. So what we actually do is we take the limit, but we take the limit essentially selectively, right? So I take the limit to average out the idiosyncratic noise, right? So here I get flows, but in terms of having n agents, I stick with n agents. So this hybrid, where we're essentially averaging out the idiosyncratic noise, but keeping a finite number of agents for calculating market equilibrium, turns out to be a very parsimonious way to handle these kind of asset pricing problems. You're looking very quizzical, Andre. No? OK, sure. OK. So second question, which variables would you represent with a neural network? Would we want to approximate the V? Would that be your first guess? Or try something else? What do you think would make sense to try to approximate by the neural network? Well, we're late in the day now. So in the end, we approximated the consumption to wealth ratio, right? Why do you think approximating the consumption to wealth ratio might be a parsimonious way to help the neural network? Any thoughts? So in general, if you want to try to help the neural network, not necessarily what all the people in deep learning do. Many people just try to take the big set of equations and find the robust algorithm. But if you want to try to help it, you would like to try to find functional forms that it's easier for the neural network to fit. So if we think about the derivative of the value function, it's often easier to work with the derivative of the value function than the level of the value function, because it's very easy to impose things like concavity and certain properties of V, right? We can actually impose that in the structural form of the neural network. It's even better to work with the consumption to wealth ratio, because when we try to get the derivative of the value function, we can actually walk back through the Euler equation, and we can get it where we have the approximate consumption to wealth ratio. Then we take your wealth share, and this gives your wealth level, and then we raise it to the power of negative gamma. Right? So the reason this helps is a lot of the extreme curvature in the problem is as handled analytically. Right? The neural network doesn't necessarily find it easy to have unbounded or very steep or explosive functions. Right? But the consumption to wealth ratio is a pretty well-bounded object. And so now we're approximating a well-bounded object, and we're imposing analytically a lot of the extreme curvature. And this helps a lot for the neural network to speed up the learning process. OK. And then finally, which equilibrium conditions we want? Well, in this paper, we tried to avoid market clearing. There is some debate. I think Marlon and Jan would agree that avoiding the market clearing conditions is a good idea, trying to keep them out of the loss function and instead imposing them explicitly. But not all papers find the same thing. That's at least what we've done so far. Okay. Questions so far? How many people have trained a neural network before? Okay. How many people have trained a neural network to solve an economic model? I see. So you trained it to solve a statistical model. Okay. Is it making sense, what I'm suggesting? Okay. Well, it's, sorry, the question was how do you know that imposing it in the sampling impose it in the equilibrium? Yeah, so we've had the same question our writer was quizzing us on. So maybe it's not the best way to say it, right? So I think perhaps a better way to say it is rewrite there is redundancy in the state space once you impose all the equilibrium conditions. And so you can kind of rewrite the state space in such a way that equilibrium is imposed, right? And so we're working in some sense with the quote-unquote master equation, right? So the master equation is once you've actually imposed all the equilibrium conditions and placed that constraint on the way everything moves and the co-movement between different states. And once you've done that, you can simplify the problem, right? That's the idea. So perhaps imposing in the sampling is not the best way to say it. I think imposing cross-equation restrictions across the state space so they always hold might be a better way to say it. Does that make sense? Okay. All right. So how long do I have, Markus? Till 5? Okay, so we're doing okay. So once we do all that, we need to think about an alternative characterization of the equilibrium, okay? So based on what I just said, we want to change the variable to the marginal value of wealth, okay? And we want to work with a different state space, right? So it turns out to be much easier to impose all these equilibrium conditions when we're working with wealth shares rather than wealth levels. So I think you guys kind of know that because that's what you've been doing the whole time here. So we work with the wealth shares across all the agents in the economy. Okay. So once we do that, at a particular state, we have a whole lot of objects we care about: the derivatives of the value function, the prices, the consumption to wealth ratio, which gives us or relates to the XIs, the volatility of the drift and volatility of the state, plus all these other objects. Okay. And essentially, they're going to solve an Euler equation, right? So this is the derivative of the HJB with equilibrium imposed. And we're going to have a belief consistency, right? So we need the volatility of the price process to satisfy Ito's lemma. Plus, we need all the first order conditions and wealth share evolution, KFE equations to hold with the equilibrium imposed throughout the whole system. Okay? So that's the thing we want to take to the computer. Okay? So how do we, yes, go for it. So the question is, if I have the derivative of v to a, how do I recover the derivative of v with respect to the other variables? So here we don't actually solve for the value function. We're only ever going to solve for the derivative of the value function with respect to a. And then but along the way, we're necessarily going to solve for the cross derivative. So we're going to solve for the derivative with respect to a and z, the derivative with respect to a and all the different etas. But we do not actually recover the value function. Right? So we can go back and integrate, but what we're actually going to take to the neural network to solve is the derivative of the value function. So this is an asset pricing room. So essentially, we're approximating the SDF, right? This is an asset pricing model. We're going to get the neural network to fit the SDF, and we're going to use that to solve the system. And that's what we're kind of working with. Does that make sense? Okay. All right. So this is very similar to what Gautam had. So we're going to approximate the consumption to wealth ratio and the sigma q by the neural networks. We approximate these two objects because once we approximate those, we can solve for the rest of the equilibrium analytically, right? As a linear system of equations. So this means that at any given state, the error or loss in our neural network approximation is given by the loss in the Euler equation with the consumption to wealth ratio plugged in for the xi, and the loss in our consistency equation on sigma q. Right? These are the two things we're going to try to minimize, very similar to what Gautam had, although the difference here is we've taken the market clearing out of the loss functions. We've imposed that analytically throughout this system of equations. Does this make sense? So we need to train the neural network to learn the omega hat and the sigma hat. They're going to minimize these things. Okay. So the algorithm would look something like this. I initialize the neural networks with an initial set of parameters, capital theta. Each iteration, I'm going to draw a set of new training points, right? So I need to sample from Z, sample from K, sample from the distribution eta. At each training point, we can calculate sort of the current guess of the consumption to wealth ratio and the volatility of Q. We can then step through and compute equilibrium. We can compute all the consumption to wealth ratios. We can compute the prices, get the portfolio choice, compute all the drifts. And then once we've got all these objects, we've got the full equilibrium on those training points, and we can then evaluate the loss for omega and the loss for sigma. Okay? And then we update using all the fancy stuff Gautam was talking about in the last talk. I don't have any fancy 3D graphs showing the movement to the local minimum. We haven't tried to plot the n-dimensional loss function here. It would be a complicated object, but maybe some of you can peer into n dimensions and see it nonetheless. Does this make sense? Okay. Out of interest, how would you think about sampling from eta, right? So eta is kind of the distribution. What might be some options? So sampling from the distribution is probably one of the trickiest parts of trying to get these high-dimensional deep learning problems to work. Any thoughts on how you might sample a good set of distributions? Well, what's the problem with just trying to do it completely randomly, right? I just pick completely random etas from a uniform distribution or something like that. Why might that be a bit hard going for the neural network? Right. I mean, yes, sort of. And I think where you're kind of heading a little bit is I don't care about all distributions, right? There's a lot of distributions we'd never see. So suppose I have like a 200-dimensional distribution, and then I'm trying to learn every conceivable combination. It's just too long, right? And it's useless, right? A lot of them I don't care about. So we need to find ways to try to sample the distribution from distributions that look similar to what we would like. So we might at least want to move the mean in a space we're interested in, right? In these kind of asset pricing models, you care a lot about the mean of the distribution. That relates a lot to the portfolio choice in capital. You might want to move the mean systematically in a range and then fan the distribution out. You might also want to solve for something like a steady state distribution. You could solve for it in different aggregate states and then take perturbations between those steady state distributions. That's what we do in all the search and matching models. Or you could if you wanted to try to simulate, right? So you could take the current guess, simulate the economy, look at distributions on the simulated path, and then feed them back in for training points. So a lot of options for how you should think about trying to sample from the distribution. I would say often when things are not working well, trying to change that sampling makes a big difference. The search and matching models we were doing really had a lot of trouble solving until we nailed the right way to get the sampling. And then they worked much more cleanly. Okay. All right. So we can make a couple of comments here about asset pricing and inequality. Right? So let's start heading back a little bit towards economics. So if we think about the evolution of the drift of wealth between different agents in the economy, we have a pretty nice expression for what this looks like, right? Agents here do not all have the same portfolio choice, right? Wealthier agents end up with more capital stock, and poorer agents end up with less, right? So the difference in your holdings of capital, that depends, if you hold more capital, you can earn more of the excess return on capital, and that changes your relative wealth, okay? Likewise, there's potentially differences in the way you consume, right? The consumption to wealth ratio appears in blue, and then potentially we have any kind of distribution scheme coming from the agents dying and then being reborn. Okay? But in particular, we have this participation constraint, right? That low wealth agents are less able to get involved in the financial market. If we think about having sort of a quadratic cost, where this psi bar is the severity of the constraint of trying to get involved in the capital market, this means that lower wealth agents have a lower share in capital, are less able to earn the capital risk premium in the economy, which has a big impact on the evolution of the distribution. So here I've got just an illustrative example. So the different colors correspond to different severities of the household participation constraint. So the blue line is when there's very little participation constraint, the households can almost freely hold capital. And the green line is when we have a much more severe participation constraint. On this axis here, I have the wealth share of a particular household. So we can see that as they get wealthier, they increase their share in capital stock more. And the lower the participation constraint, the more they increase their share in the capital stock. Makes sense, right? Then we have a whole bunch of other things that are based on the wealth share of the expert, right? So we've got the wealth share of the expert on all the other x-axes. In this final one, we have the drift of the wealth share of a particular household versus another one, where I is a household that is 10 times wealthier than household J. And so we can see here that how the wealth of the banker relates to the opening up of inequality in the economy is very related to participation constraints in the economy. So if we take the economy, the green one, where the households are very constrained in their ability to get involved in the capital market, that means that when A to E goes low, when the wealth share of the expert goes low, the households cannot really easily get involved and try to buy the capital. So the experts are forced to hold capital they don't want to hold, so the risk premium in this economy shoots up. Right? There's this big increase in the excess return on capital to incentivize the experts to hold it. That's really great for the few households that can also participate. Right? If you happen to be one of these wealthier households that are able to get involved when the experts are in trouble, you earn a really big excess return, and so you get this big expansion of inequality. On the other hand, if we have the economy where the participation constraint is much milder, then when the experts get poorer, the households can much more easily step in and buy the capital, so the excess return does not open up as much, and so inequality does also does not open up as much. Okay? So you see this very tight link between the ability of the households to participate and inequality, and it works through who is able to take advantage of the risk premium. Right? You spent the past 2 days talking about models where the wealth share of the financial sector really determines the risk premium. Well, once we put a distribution of households in, if you care about inequality or you care about household welfare, you'd really care about who actually has access to trying to earn that risk premium. And the answer is not everyone, and that has big implications for the way financial instability relates to inequality. Right? When you have wild swings in financial situations, right, a really volatile economy, it opens up big opportunities for the wealthy households that are very able to get involved in the financial markets directly. Does this make sense? Questions so far? You're looking forward to dinner. Okay, yes, go for it. No, actually, it's not necessary for this result at all. That's only necessary to get a stationary wealth distribution. We've had some debates. I mean, when I look at the data, it's not entirely clear to me, and I think Gautam would agree, it's not entirely clear to us that there is a stationary wealth distribution. It kind of looks like inequality is increasing, and then there's a huge war and inequality drops down or something like that, right? It doesn't look like the most stationary process, at least in the short run, right? So if you took out the transfers, you'd get something that looks a lot like that. We actually did this exercise where we just calibrated the asset pricing and said, suppose there are no redistribution transfers and the rich get richer and the poor get poorer, how well does it do just capturing the inequality increase over the past 40 years? And it does a pretty good job. Right? So in that sense, I think we would have some sympathy with the idea that the transfers are not all that important economically. But if you want a stationary wealth distribution, you need something that will start to bound it. The consumption difference does it a little bit, but here that really controls the stationary distribution. Does that make sense? Okay. Okay, so last little bit, let's get to the richer model. Okay? So it's very similar setup. So again, it's continuous time. Okay. So we have a goods technology again. Here we're going to introduce an extra shock, right? So in addition to having the TFP shock, we're also going to have that the volatility of TFP also follows a stochastic process. Okay? So it's a stochastic volatility model. We've got two aggregate shocks, one that hits TFP, one that hits volatility. Again, we have the continuum of OLG households. The only difference here is that when agents die, we actually have that they consume at death, right? So you don't just consume during your lifetime. When you die, you want to consume a mass of consumption, right? We interpret this as a reduced form way of thinking about your lifetime retirement, right? You get to your end of life, you want to do a big consumption, you need some way to finance that. Okay. Otherwise, it's a very similar model. What we are going to change, though, is the financial sector. So now we have both a fund and a banker. Well, first of all, we have a government that issues bonds, right? So we're going to introduce long-term government bonds into this economy. Then we have two types of financial intermediaries. We've got a fund that offers pensions that help insure this death risk, right? So what these funds offer is they offer a sort of pension/insurance contract that pays one good to the household holding the contract when they die, okay? So it's directly trying to provide them with consumption to cover this need to consume at death, right? That's what these contracts do, okay? We also have bankers, and the bankers issue short-term deposits, okay? So we've got two different types of liabilities, deposits issued by the bankers, pension insurance contracts issued by the fund. And then on the asset side, they can potentially hold capital, they can potentially hold bonds. So now we have three long-term asset prices. We've got a price of capital, a price of these contracts, which I'm denoting by N, these insurance pension contracts, and the price of long-term government debt. Does this make sense? Okay. So we've enriched the model to give a little bit of a sense of the change in asset pricing. So now when we think about all our first order conditions, we get distortions coming from this need to get these insurance products at death. So if we think about these pension insurance contracts, now instead of just balancing the excess return against the co-movement of the SDF and prices, now the agents also think about whether the contract is going to help them finance this consumption at death/retirement. Okay? So this is the special benefit these pension products provide, which gives the pension sector this kind of cheaper source of financing. Okay. If you're interested in Vianis-Filler, this nests a Vianis-Filler model, although I don't think you guys did the Vianis-Filler model in this, so I'm going to leave that. Okay. And then the capital market is similar, although of course when the funds participate, they're now exposed to different types of shocks, right? So the bank has deposits that are not exposed to TFP or volatility shocks. They're just promising one no matter what. Whereas the fund has these pension annuities that actually increase with TFP and decrease with TFP volatility. So the way their SDF naturally moves with respect to these different shock processes when they try to price the capital looks very different. Okay, so this is the richer model. The question we want to think a little bit about here is how are the households affected when the government restricts which assets the funds or the bankers can hold, right? This is going back to the question we had at the start of the class. If I choose a particular segmentation of the financial sector, what happens? Okay. So this means that when we think about this evolution of household wealth inequality, we now have an extra wrinkle, right? We have to think about the different portfolio shares in capital, but also the different portfolio shares in the fund. And the reason this matters is if the fund ends up in trouble, the way it's going to recapitalize is by earning higher premiums on its members. And so who it is that is in the fund when it ends up stuck or when it ends up in distress is going to have a very big impact on inequality. Right? And the issue in this economy is if we look at the theta K and the theta N, the low wealth agents are not very involved in the capital because it's hard for them to get involved in the capital market. Instead, they go through the pension sector, right? So these are people, the poor agents, they have a 401k instead of having their own Tesla company. So they are less involved directly in the capital market. And so essentially it's the poorer agents that are going to be the ones that are very exposed to what happens to the premiums in the fund sector if the fund ends up in trouble. And that's what gives this kind of ambiguous impact on how this segmentation of what can happen affects inequality. Okay, so I've got a little bit out of time, so I'm just going to summarize the key results here. Okay? So the first question is, in this bigger model, how do we find risk is allocated between households, bankers, and funds if we allow it unregulated, right? So if we're neither the 19th century nor the 20th century, we go back to the laissez-faire, and all the intermediaries can do whatever they want, right? In that world, in that unregulated economy, these funds do absorb a lot of the risk, right? Particularly when the funds are well capitalized, they absorb the risk from the banking sector by buying capital and from the household sector. This is because they have liabilities that are a natural hedge against the business cycle shocks. Right? These long-term liabilities they issue go down in price in a recession, increasing their net wealth in the recession. Okay, that's great. The difficulty comes, though, that if these funds then become distressed, right, because they're taking on a lot more risk in the economy, they end up having to charge higher premia in order to rebuild that wealth and recover. And the question is, who wins and who loses from that? Well, it has a lot of impact on household welfare. So if we restrict the fund from being involved in the capital market, so we follow FDR and we say, let's try to get the banks to do more of that, let's try to scale back a little bit the extent to which we have pension and insurance funds kind of owning a lot of the risk in the economy, then we get that it does help low wealth households in the sense they don't have to end up paying these premiums because the fund sector is not as risky. Okay? We also have that the regulation really increases the price of government debt because you create a very captive market for it in the pension insurance companies, which is also what we see. Generates a big convenience yield in this model. Okay. So there is some sense in which the changes did make sense, in the sense if it's really the participants in the fund who are lower wealth that are really forced to recapitalize the funds, there is some benefit to trying to segment this market. Okay, I think I'm exactly on time, is that right? You said till 5? So I'm going to end it there. So I think the economics lesson here is we should study how the government chooses asset market segmentation strategically, right? Some of these results at the end are a bit preliminary. It's not a fully calibrated model yet. But I think the message you should take away is the government has very frequently throughout its history chosen to shut different financial intermediaries out of different markets. It wasn't an accident, right? This is not some fundamental environmental friction in the economy. This was a strategic choice by the government for a reason. And we should think harder about what those reasons really look like instead of writing down models where you just say there's segmentation and leave it at that, right? So the push here is to try to think about the design problem of the government in the way they shut different types of agents out of different types of markets. It's not an easy thing to do, and the technical thing we bring to the table is training the neural networks. So here we can solve models with a large number of heterogeneous agents. We have financial frictions that prevent kind of a closed form value function, and we have multiple long-lived assets. Not an easy model to solve, but I hope I've made a little bit of progress in persuading you. There's a pathway forward here to think about institutional finance and macroeconomics together, something that we have not been able to do up till now. Okay, thank you very much.